Today, we're going to review material for exam 6, which will be due, I believe, on the 28th of, yes, due on the 28th of March, 2 days from today. And as usual, I'm going to work from the review document, and I've highlighted some problems that I want to be sure and cover. So let's get started. We have number 1. How many grams of calcium chloride are needed to prepare 5.17 liters of 0.5 molar calcium chloride solution? This is a solution preparation problem, right? If you know the formula for molarity, that's the point we start at, right? Molarity is moles per unit volume, and the volume must be in liters. All right, so the target concentration is 0.5 molar. And the final volume we need is 5.17 liters. Right? And the unknown for this part of the problem is moles. But the question is not how many moles, how many grams. So once you find the moles, you can use molar mass to determine the grams. Now we can do it in 2 steps, or we can substitute the equivalent of moles in here by calculating, using a formula for calculating the moles of calcium chloride. But I think that's a little too much for this class. Let's find out the moles first. Right? Solve for N, that means 0.500 molar times 5.17 liters is equal to the number of moles we need. And that's 2.585 moles of calcium chloride. Now you may notice we got 3 significant figures here, 3 significant figures there, and I kept 4 here. The reason I do that is because the next calculation, when I do the next calculation, I don't want to introduce a rounding error. So I'm not going to round it yet. All right, so if we have that many moles, right, we need a conversion factor that will give us grams. That's our answer. And this unit goes in the numerator, this unit goes in the denominator, and we need grams per mole. And it's given to us right here in the problem, 111 grams per mole. Moles cancel, and now my calculator tells me 286.935. Now remember the rules for significant figures. There's one set of rules for multiply, divide, and another set of rules for add, subtract. We had no add, subtracts in here, which means all we have to do is find out what's our starting point. Our starting point is 3 significant figures. Then at the end, we can round to 3 significant figures. Right? And that's our answer. So in this case, B is the choice. All right. Okay, number 2. What mass of solute is contained in 64.9 milliliters of a 2 molar sodium bromide solution? We're using the same formula as before. The question is, what mass of solute? Right? So in this case, we want to solve for the number of moles. If we know the volume and the molarity. So if we solve for moles, that's molarity times volume. And molarity is given as 2 molar. But the volume is in milliliters, 64.9 milliliters. Right? How many liters is that? Well, if you're familiar with what does milli mean? Milli means 10 to the minus 3. So 64.9 times 10 to the minus 3 liters. Or we can take 10 to the minus 3, which would be 3 decimal place moves to the left. Right. 1, 2, 3. 0.0649 liters. Now we can find out how many moles, but that doesn't answer the question. That's only halfway there. That's 0.1298 moles. And then we want to convert that to mass. And for that, we have to calculate the molar mass of sodium bromide ourselves. That's where you go back to a previous chapter where we learned how to name compounds and write their formulas. And at that time, I told you, you're going to need this in the future. So you better learn it. Sodium bromide is 1 sodium plus 1 bromide minus. So now we can add up sodium and bromine. 23.00 grams per mole for sodium. And then bromine is 79.90. Right? 0, 9, 12, 102. 102.90. So now we can convert moles to grams. 102.90 equals what? So I get 13.3564 grams. And we have 3 significant figures here and here. So we round it off to 13.4 grams. Okay. All right. This works any better. Nope, it didn't work any better. All right, number 3. And I've got myself some notes here. Number 3, we use the exact same conditions for number 6 as number 3. So I'm going to go from 3 and skip to 6 as soon as we solve number 3. All right, you have 3 liters of 3.67 molar solution of sodium chloride. That's called solution A. You also have 2 liters of a 2 molar solution of silver nitrate, solution B. You mix these 2 solutions together to make a solution C. What's the concentration of silver ions in solution C? All right. Let's put let's build the problem first. We're reacting sodium chloride in aqueous solution plus silver nitrate, also in aqueous solution. And what are we going to get? This is a double replacement reaction where the sodium replaces the silver. So we're going to get sodium nitrate and we look it up in our chart, right? Our solubility chart. And I'm not sure where, let's see. Yes. The review document has the solubility chart right here in the back. All right, there it is. All right. So remember, cations across the top, anions down the left-hand side. You find out where they meet and see if it's grayed out. If it's grayed out, then they're not soluble. If it's clear, they're soluble. We find that sodium nitrate is soluble. What's left over? Silver with chlorine. Oops. Try that one again. Silver, chloride. And we look that one up, and that one is insoluble. Next thing we have to do is balance the equation, or verify that it's balanced. We have one sodium, one chlorine, one silver, one nitrate, and one nitrate. This equation is balanced as written. Okay, other conditions. We have 3 liters of a 3.67 molar solution here. 3 liters of 3.67 molar solution. That's solution A. We're gonna add to that 2 liters of a 2 molar solution. Of sodium nitrate. And the question is, how many, what's the concentration of silver ions in solution C? Well, the question then is, since you have an absolute amount of this reactant and that reactant, we have to determine which one of those is limiting. There are 2 ways to do this. And I suspect that subsequent problems are going to ask us how much silver chloride we produce. So let's use the method where we say, we're going to use all of this one and make silver chloride. Then we're going to use all of this one and make silver chloride. And we compare the 2 amounts. And the one with the least amount production will be the limiting. Right? So we need to know the number of moles of each reactant. Right? Remember, you can't move anywhere in a balanced equation unless you have moles. So if you recall, right, molarity equals moles divided by volume. We want to know moles. So moles is molarity times volume. Molarity times volume. Right? That will give us the number of moles of sodium chloride. Which is 11.01 moles. And this one is obviously 4 moles. Now we could tell from this relationship 1 to 1. This one is the smallest amount, it's going to run out. So we can save ourselves some calculations, say, we know that this one's going to be the limiting one because it takes 1 of these for every 1 of those. And once we use up 4 of these, then we're done. So 4 moles of silver nitrate will produce, while we're here, how many moles of silver? How many moles? This is moles of silver nitrate. Right? For every 1 of these, you get 1 silver. So we also start off with silver ions, that many silver ions. Okay, back to the question. What's the concentration of silver ions in solution C over here? Well, we used them all up. They're all gone. This is the limiting. That's the limiting reactant. That means all silver is gone. So there are no silver ions in solution, right? 0 molar. Okay. That would be, and our choices are C, right? So C answers that one. Okay. Now let's go to 6 and use this same scenario to answer questions for number 6. All right, in this case, we have a different set of circumstances. All right, so let's make the changes that are necessary. Sodium chloride in this case is 3 liters of 3.48 molar. 3.48 molar. Okay. And silver nitrate is 2 liters of 2 molar. Right, so 2 liters, 2 molar, that's the same. This one then would become 3 times 3.48. This one is 10.44 moles of sodium chloride. Now, what's the question? What's the concentration of sodium ions in solution C? Well, notice that we have this many moles of sodium chloride, and for every 1 mole of sodium chloride, you have 1 mole of sodium ions. So similar to this arrangement, you also have 10.44 moles of sodium ions. Now, how many do you have left after the reaction? In solution here, in solution there, you have exactly the same number of moles of sodium ions in the product solution. Because sodium and nitrate are spectators. They don't participate in the reaction. The reaction is between silver and chlorine. And we could substitute anything for sodium, like we could put potassium in there. It would get the same reaction. Okay, so we know the number of sodium ions, this many moles. And if we calculate the molarity, we have moles. Now we need volume. What is the volume in the final solution? Well, the volume is not this, and the volume is not that. The volume is the sum of both of them. So if we divide this by 3 plus 2 liters, that will give us the molarity, or divide by 5. So I get 3 significant figures. 2.09 molar sodium ions. Or did they round it off? No, that's good. This is D. Okay. All right. Let's see. It says we're also using this scenario in number 47. So we're going to scroll down to 47. So I don't have to write this on the board again when I get down there. 47. Here we go. Okay. So let's remove this stuff here, here, and here. And let's see. Sodium chloride now is 3 liters of 3 molar. Here we go. And how about silver nitrate? 2 liters of 1.84 molar. All right. This has changed. 1.48 molar. Okay. Now, what's the question? What's the concentration of nitrate ions in solution C? Well, we've got new conditions for both reactants. So we need to verify which one is limiting, right? Is this one still limiting? Well, 2 times that would be, let's see, 2 times 8, 16, 1 and 8 is 9, and then 2 moles. And this one is 9 moles. Okay, so silver nitrate is still limiting. Okay, but this is 2.96 moles of silver nitrate. Is nitrate part of the reaction? No, it's a spectator. Right? So 2.96 moles of silver nitrate starts off with 269 moles of nitrate ion. And they have the same number of moles of nitrate ion in solution at the end of the reaction. It uses up this compound, but the nitrate is free in solution, right? This particular compound is going to be sodium ions in solution and nitrate ions in solution. So we have that many moles of nitrates still in solution. We just need to know what's the total volume. And the total volume is 3 plus 2. 5 liters. 2.96 divided by 5. Which is 0.592 molar nitrate. Okay. Let's see. What did I do wrong? Hold on a second. Be sure I got the right conditions. Sodium chloride, 3 and 3 makes 9 moles. Silver nitrate, 2 and 1.84. Oops. How did I do that? Calculation error. Well, let's do that one again. Yeah, now it's 0.736. There we go. $3.68. 2 times 1.84. Oh, that's the problem. There we go. All right, attention to detail. Very important. Okay, so in that case, the answer is C. Okay, we got one more down at 52 using the same reaction. All right, let's see, anything changed. 3 and 3.77. Yeah, this changes. Okay. And silver nitrate, 2 liters of 2 molar. We're back to 2 and 2 now. Okay, so get that. Just erase this. Okay. So these are correct, 3 and 3.77 and 2 and 2. Okay. Calculate the concentration of chloride ions in solution. All right. For this one, we've got 4 moles. 4 moles here. And this one is 21, 2 and 21, 23, 2 and 9, 11. Let's see if I did that one right. 11.31 moles of sodium chloride. All right. We're looking for the concentration of chloride ions. Some of these chloride ions are used up in making the solid. So all of these chloride ions, 11.31 moles of chloride to begin. This is beginning. Now we want, or before, let's do it that way. Before the reaction. After the reaction. No. Used. How much was used? And then we get after. Okay. So we need to find out how many chloride ions have been used. Okay. This one is still limiting, 4 and 11. So we can calculate the number of moles of silver chloride. Well, actually, look at this. What's our conversion factor? The coefficients create the conversion factor. Silver nitrate moles and silver chloride moles. We have one here and one here, right? So that gives us 4 moles of silver chloride produced. How many moles of chloride ions were used? The same. Right? For every one of these, you get one of these. So 4 moles of silver chloride will produce 4 moles of chloride ions. In the solid, we used up 4 moles. Okay? So we used up 4 moles of chloride ions. That means we have 1, 3, 7. We have 7 moles of chloride ions that remain in solution, unused. They're excess. Now all we need is to divide that by the volume. Right? 3 and 2 is 5. And that will give us the concentration of chloride ions that remain in solution. .4, let's see, 3 significant 6 molar chloride. Okay. That would be D. Okay. All right. I think those are the only ones for that problem scenario. Now we can go back to the top and pick up where we left off. All right, 3. Now we're going to go down to 4. And I forgot to write the numbers up here. All right, so each time I worked a problem, you'll have to pay attention to the document to see which one we're working on. All right, number 4. The molarity of chloride in 110 milliliters of solution containing 3.22 grams of calcium chloride is. All right, so let's put up here what we have. We have 3.22 grams of calcium chloride. Okay. And we also have a volume of 110 milliliters. This is mass. This is volume, 110, 10 milliliters, final volume. And we're looking for the molarity. Right? If we're going to calculate the molarity, we need to know moles and volume. And this volume has to be in liters. Right? So 3 places to the left, 0.110 liters. This one has to be converted to moles. Right? And we're given calcium chloride in a previous problem, so let me just go look at it. 111. Grams per mole. Okay, so let's find out how many moles there are in this problem. And I get 2.901 times 10 to the minus 2 moles of calcium chloride. Right? So we can calculate the concentration of calcium chloride, right? That's not the final answer because the question is, what's the molarity of chloride? But we can calculate, well, we can do it two different ways. We can say that many moles of calcium chloride, calculate the concentration of calcium chloride, then for every 1 molar calcium chloride, you have 2 molar chloride. Or we can say, with that many moles of calcium chloride, we have 5.82 times 10 to the minus 2 moles of chloride ions. Right? Because you have twice as many chloride ions as you do formula units. So let's do it that way. Assuming I calculated that correctly. Yeah. Okay. 5.802 times 10 to the minus 2 moles of chloride ions per 0.110 liters. And I get 0.3 significant figures. 527 molar chloride. And rounding error. The problem says your answer is 0.528. But remember my rule. If you don't have any oddballs in there, like none of the above, 2 of the above, 1 of the one is false, 2 is 3, they're all correct, whatever. If you have unique answers for A through E, pick the best answer. And the best answer is C. All right. Now, number 4. Number 5, I do believe. Yes. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? Notice we have 2 concentrations here. One is more concentrated than the other, and you're only given 1 volume. This is a dilution problem. So remember, concentrated molarity times volume of the concentrated equals dilute molarity times the volume of the dilute. And the best way to keep from making an error here is to write these down in a table and then put the values in your table before you try to solve the problem. What's the concentrated molarity? 12.0. Okay. What's the volume of the concentrated? That's the question. That one's the unknown. What's the molarity of the diluted one? 0.100. And what's the final volume of the diluted? 6.71 liters. Okay. So now we can put these into the formula. Let's solve for this one. There we go. Now you can plug in the values and expect to get the right answer. Let's see. 0.100 molar. Volume of the diluted is 6.71 liter. And the concentrated is 12 molar. Okay. So let's do a quick cipher on this one. and 12 divided. So I get, let's see. Notice that the answers are in standard notation. So whatever, I've got my calculator set up for scientific notation, I'm going to have to convert it in my head. And I find that it's 0.0559 liters. Okay. Now, just as a side note, most glassware in the lab is calibrated in milliliters. So if you need to know milliliters, what do? You just move 1, 2, 3 to the right. 5.9 milliliters. And notice, check yourself. The units of measure are what? They're getting smaller. Smaller units of measure means bigger number. So this number has to get bigger. That's just to check yourself, right? See if you didn't move the decimal the wrong direction. All right, so that one is A. And moving to the next problem. Skip 6, we've already done that one. And we're going down to 9. You have 3 ammonium sulfate solutions on a lab table in front of you. All of the solutions came from a 500 milliliter volumetric flask containing 3 molar ammonium sulfate. Solution 1 has 127.2 milliliters of the 3 molar solution. 2 has 68.7 milliliters and 3 has 32.4 milliliters. How many moles of ions does solution 2 contain? Right? They're blowing blue smoke in your face, trying to confuse you with multiple solutions when all you need to do is focus on solution number 2. Right? So solution number 2, right? Solution 2 is composed of what? 68.7 milliliters of 3 molar. Okay. Now the question is, how many moles of ions does solution 2 contain? Well, in order to answer that question, we have to know the formula of ammonium sulfate. Ammonium is a polyatomic ion. And sulfate is also a polyatomic ion. This one has a 1+ charge. This is a 2- charge. That means we need 2 ammonium ions. Right? So there's your formula. And how many ions for every one of these? You have 2 + 1 is 3. You have 3 ions per molecule. Okay, actually, that's not molecule. Per formula unit. Okay. All right. How many moles of ammonium sulfate do we have? Well, this needs to be in liters, doesn't it? Right. 1, 2, 3, 0.0687 liters times 3. So that's 0.2061 moles of ammonium sulfate. You want to know how many ions? Right. This is moles of formula, moles of ions. So for every 1 formula unit, you have 3 ions. So 3 times that is 0.618 moles of ions. And that means the answer is E. All right. That was number 9. Number 10. Simple fill in the blank question here. A mixture of sand and water is what? Is it a solution? No. It is a mixture, but it's a heterogeneous mixture. It's not a solution. A, it's not an aqueous solution. It's not a B, a solution. It's not a solute and it's not a solvent because it's not a solution. Neither one of them. Right? It's none of these. A through D give you no information about a mixture of sand and water. Let's move on to number 11. A chemist needs 225 milliliters of 3.1 molar HCl. What volume of 12 molar must be dissolved in water to form this solution? All right, this is another dilution problem. Right, so we're going to have concentrated, let's take it in order. Molarity of the concentrated, volume of the concentrated, molarity of the dilute, volume of the dilute. So let's put our values in the correct place. The chemist needs 225 milliliters of this concentration. Of what concentration? 3.1 molar. And he's starting with 12 molar. And the volume that he needs to dilute to 12 molar to 225 milliliters is the question. Okay, so now we have concentrated, dilute. We're going to solve for this one. Okay, molarity of the dilute is 3.1. Volume of the dilute is 225. And concentrated molarity is 12. Okay. Notice I didn't change the units of volume. The reason you can do that is because this is a ratio, right? That volume and that volume have the same units of measure. It could be liters, it could be milliliters, it could be ounces, it could be gallons, doesn't matter. If you start off with this many, or this unit of measure in one of the volumes, the other volume is going to be the same units of measure. All right, so let's say 3.1 times 225 divided by 12. And this is 58.1 milliliters. Oh, they're rounding it off. So the best answer here for that one is E. Okay. All right, that was number 11. Let's see. Number 13. I need a new marker. All right. You have 250 milliliters of 4 molar sugar solution. You add 376.3 milliliters of water to this solution. What's the concentration of the sugar solution after you add the water? This is still a dilution problem. Only you have to be careful determining what goes in these variables. Okay. The molarity of the starting solution, the concentrated solution, we know it's going to be the concentrated because we're going to add solvent, which will dilute it. So we're starting with a concentrated solution of 4 molar. Right? And the amount of the concentrated solution is 250 milliliters. Okay? The question is, what's the concentration after we dilute it? Now, here's the trick. What is the diluted volume? The diluted volume is the original volume plus the added volume. Okay? So that value is going to be 250 plus 376.3. And that's 626.3 milliliters. Now we can solve the problem. Solve for molarity. Well, let's see. Let's put it up here like this first. Volume concentrated, molarity dilute, volume dilute. Then we solve for this one. Okay. Now we can put our values in. Concentrated molarity is 4.00. Volume of concentrated is 250 milliliters. And volume of dilute is 626.3 milliliters. Now, that's the thinking part, right? The rest is number crunching. All right. I get 1.5967 molar, but we've only got three significant figures. So let's round it. 1.60 molar. That would be B. Okay. That's the trick. Figuring out what the final volume is. 14. Okay. Excuse me. You have two hydrogen chloride solutions, which would be hydrochloric acid. Labeled solution A and B. Solution A has a greater concentration than solution B. Which of the following statements are true? So let's put what we know up here. Right? We have two solutions of hydrochloric acid. Solution A and solution B. Okay. Solution A has a greater concentration than B. So the molarity of A is greater than the molarity of B. That's what we're given in the problem. So let's look at our statements. If you have equal volumes of both solutions, solution B must contain more moles than HCl. Well, what is this equal to? That's equal to, molarity is equal to moles of actually moles of HCl per liter of solution. And this one has so many moles of HCl per liters of solution. Right? So the first one says A says if equal volumes, right? If, let's do this. Let's say volume of A, volume of B, so we can keep them straight. If you have equal volumes, if V sub A equals V sub B, then not what does the question say, but what is the reality about the number of moles? Well, look at this. Volume of A equals M sub A times N. And this one would be volume of B equals, excuse me, that's not right. Moles of HCl divided by, there we go. That's correct. Yep. So this one would be moles of HCl per molarity of B. Okay, now, if these two volumes are equal, but this one is bigger than that one. Remember, when you have two variables that are in a quotient, like this, and they're equal to a constant, this is the same as that one, so it's considered a constant. If you have a quotient of two variables, they are always directly proportional. If one goes up, the other one has to go up. So if these two are equal, but this one is bigger than that one, then moles must be bigger than those moles. Right? So moles of A, HCl, must be greater than moles of B, HCl. Is that what the problem says? If you have equal volume, solution B must contain more moles. No, that is false. We just proved it. How about B? What's going to happen with B? Adding more moles of HCl to both solutions will make them less concentrated. Well, that's just crazy. If you add more solute, you're increasing the concentration. So B is false on its face. Can't be. C. To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. Well, look at it. The concentration of B is already less than the concentration of A. If you add more solvent, you make it even less concentrated. Right? So C can't be right either. How about D? At least two of the above statements are true. D should be in E's place, and they should be swapped. Because D talks about all of the conditions, and we haven't even got to E yet. So what does E say? E says, if you have equal moles of HCl in both solutions, equal moles. All right, let's solve for moles now. Moles of A, HCl, equals moles of B, HCl. Well, what is each one of these equal to? Well, now, this one is equal to molarity times volume. Okay? And this one is equal to its molarity times its volume. Okay. Now, if these are the same, which means they represent a constant value from here to here, and we have a product of variables, then these variables must be indirectly proportional. Think about it. If that's constant, if one of these goes up, the other has to go down. Otherwise, that is not constant. So now we're saying with E, if you have equal moles in each one, solution B must have a greater volume. Equal moles, but this is bigger than that. So that means this must be smaller than that. If this is greater than that, then this must be smaller, must be greater. So the volume of B must be greater than the volume of A. This one is true. E is your answer. Right. Okay, scroll to the next one, 16. A 116.9 gram sample of nitric acid solution that is 70% by mass, HNO3 contains how many moles of HNO3? All right, what do we have? Well, we've got 100, the mass of the solution is equal to 116.9 grams. And this solution is 70% HNO3 by mass. 70% mass is the way we would write that. So what does that mean? That means for every 100 grams of solution, you have 70 grams of HNO3. That's what that means. Okay, if you have this mass of solution, then we have our conversion factor right here. 70. Actually, that's only, yeah, 3 significant figures, right? 70 grams of HNO3 and 100 grams of solution. So the solution, this is solution. Solution cancels and leaves us with grams of HNO3. Now, that doesn't answer the question, but it does get us part of the way. Because if we know the grams of HNO3, we can calculate the moles based upon the molar mass. So let's see, 116.9, is that correct? Yep. Times 70 divided by 100 is 81.83. 81.83 grams of HNO3. Now we need to convert it to moles. We need the molar mass of HNO3. Right? Hydrogen is 1.01 grams per mole. Nitrogen is 14.01 grams per mole. I'm pretty sure. Yeah. Oxygen is actually 3 times 16. Okay. Now we can get the molar mass of HNO3. 3 times 16 is 48, and 14.01 and 1.01 is 63.02. So 63.02 grams per mole divided into 81.83 is 4 significant figures. 1.298 moles of HNO3. Okay, so it was rounded off to 3 places. I'm not sure why. Oh, 70%. That's only 3 places. So if we round this off to 3, right here, then 8 makes this one 10, carry your 1.30 moles. That's correct. 3 significant figures. All right. 17. Okay. Determine the normality of a base of 93 milliliters of 1.8 molar HCl is required to neutralize 52.0 milliliters. All right. Remember, normality is based upon, for acids and bases, is based upon the equivalence per liter. And the equivalence could be hydrogen ions or it could be hydroxyl ions. So what we're dealing with here, let's put what we know. 93.0 milliliters of 1.8 molar HCl. So the volume of acid is equal to 93.0 milliliters. The molarity of the acid equals what? 1.8 molar. 1.8 molar. Well, notice that hydrogen chloride only has one hydrogen. That means molarity and normality are numerically identical. So we can say the normality of the acid is equal to 1.8, normal. Right? Like that. That's not nitrogen, that's normality. Now, how about the base? Let's see, the base is 52 milliliters of base. Volume of the base equals 52.0 milliliters. And now we're going to solve for the normality of the base. Now notice that once you have the normality, it doesn't matter what the acid or the base is. That's been taken into account when you calculate. So that's why the question is calculate the normality of the base. We don't care what the base is. Not for the calculation. So normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. Okay. Normality of the acid is 1.8 normal. Volume of the acid, 93.0 milliliters. Normality of the base is our unknown. Let's go ahead and solve it for, let's put the volume of the base over here. Right? Volume of the base, 52.0 milliliters. Okay, I just solved the equation, substitute the values at the same time. So now we can do the calculation. 1.8, 93, and 52 divide. And we have two significant figures. So I'm going to round it off from here is 3.2 normal base. Okay, and that's B. That's B is the correct choice. All right, that was 17, 18. Magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. All right. Well, let's put that reaction up here. Magnesium metal plus hydrochloric acid yields what? Magnesium chloride. And that should be soluble. Yeah. But I didn't write that correctly. Magnesium is an alkaline earth. It's a 2+ charge, and chloride is a halide with only 1- charge. So we need 2 chloride. And then hydrogen gas. Okay, now let's be sure it's balanced. 1 magnesium, yep, 1 magnesium. 2 hydrogens. We need 2 hydrogens. And that gives us 2 chlorines also. So now it's balanced. And we didn't even have to put the budget together. Okay, now what else are we given? Suppose we have excess metal. Excess. Okay. And with 19.8 milliliters of 3 molar solution. Okay. And we collect all the hydrogen in the balloon. So we're going to collect all the hydrogen here in a balloon at 25 degrees C. Temperature equals 25 degrees C. And 1 atmosphere. Pressure is 1 atmosphere. Okay. What's the volume of the balloon? So the volume is actually the question. Now let's work backwards. If we're going to calculate the volume of this gas, oh, hold on a second. I don't think we've talked about gases yet. No, no, we haven't. We can't solve this problem because I haven't told you how to resolve this part of the problem. So throw 18 out. 18 is no good. I could solve the problem for you here, and then when we get to gases, you'll see the relevance. I guess we could do that, right? So we'll go ahead and do that because this is a stoichiometry problem. If we need to know the volume here, we need an equation that will give us that, and we're going to learn that in chapter 13, I believe. Yes, chapter 13 on gases. All right, and that equation is pressure times volume equals moles times a constant times temperature. And the temperature has to be in Kelvin. So we add 273 to it, and we get 2 Kelvin. Atmospheres, volume will be in liters, and R, let's just solve it for volume. Volume equals nRT over V. And that's going to be, we need to know the number of moles, so that's where the stoichiometry comes in. We're going to save a place for the number of moles. 0.08206 is R, and temperature is 298 K divided by volume. Oh, no, we got volume, excuse me. That's wrong. This is pressure. Pressure, 1 atmosphere. Okay, so we got to fill in that number of moles here. All right. Now, to calculate the number of moles of hydrogen, we need to know the number of moles here. Okay. So this needs to be 0.0198 liters times 3. Which is 5.94 times 10 to the minus 2 moles of HCl. We want to know hydrogen, right? So we need a conversion factor to convert HCl to hydrogen. And the ratio is 1 coefficient to 2 coefficient. So just take half of that. And that's 2.97 times 10 to the minus 2 moles. So that's what we put in here, moles. 2.97 times 10 to the minus 2 moles. Times 0.08206 times 298 and divided by 1. So the volume is going to be 0.726 liters. Okay. Now, you wouldn't know how to solve this problem because you don't know the gas laws, right? But I went ahead and did it so that when we do get to the gas laws, it'll be familiar to you. But you don't have to know it for this test. Unless I put an extra credit. If you paid attention, then you'll be able to solve it. But moving on. All right. Number 22. All right, which of the following solutions contains the smallest number of ions? All right. This is where I'm going to use Henry Ford. Set up an assembly line. So we've got, let's see, A, B, C, and D. And then E says 2 of the above contain the smallest number. So they'd have to be exactly the same, right? If they both contain the smallest number. So remember, molarity equals moles divided by volume, and moles equals molarity times volume. That will give us the number of moles of the compound. but we need to know how many ions are in each formula unit. All right, so that's the first thing I'm going to do. Sodium sulfate is the first one. Lithium nitrate. Lithium is an alkali metal. Nitrate is a 1- charge. So that's it. Potassium hydroxide. And iron 3 chloride. So iron 3 plus and a chloride 1- means you have 3 of those. Okay. So there are our 4 compounds. What's the concentration of the formula unit first? And then we'll convert it to the number of ions. Well, if we multiply molarity for each one, 1 molar, 1 molar, 2 molar, 2 molar, 1 molar, 1 molar, 2 molar, 2 molar, times volume. And in this case, we're comparing relative amounts. So I'm going to introduce a new unit of measure, 246.8. 246.8 milliliters. Molarity times milliliters equals 246.8 millimoles. All right. And let's see, the next one is 539.8. 539.8 milliliters, which again will be 539.8 millimoles. And this is of the formula. Okay. And the third one is 305.6. 5.6 milliliters, which equals, let's see. So I can do this on my head. Say 1/10 11 and 1/6 millimoles of formula. And the last one. 189.6 milliliters. 2 times that. Okay, 12. Carry the 1, 19, carry the 1, 16, 17, carry the 1, and 3. All right. That's the number of millimoles of each of the formula units. How many ions do we have? That's why I call it Henry Ford. Solve it by Henry Ford's method. We've got an assembly line here. We do the same thing over and over. We might substitute a part or two on the automobile, right? Come off the line with a slightly different automobile, but the process is the same for every one. All right, so we're going to have formula here. And ions here. Why? Because we want to cancel the formula and leave us with ions. So what's the magic number? Well, how many ions do you have per formula unit here? 1, 2, 3. 3 to 1. How many here? 1, 2. 2 to 1. How many here? 2 to 1. And how many here? 1, 2, 3, 4. 4 to 1. Okay. All right. So if we multiply 3 times this one, that's about 750. And we have 2 times this one is about, let's see, 1080 millimoles. I'm just estimating because I don't need to know the exact number if I'm only comparing them. 2 times 6, that'd be about 1200. Right? Approximately. And 4 times 379 would be like 1500. Roughly. let's see, 4 times 8, 32, 3. That's closer to 1,600. Okay, by comparison, we only need to know the smallest amount. That's this one right here. This gives us the smallest number of ions. And if you do it assembly line way, then you're less likely to make mistakes and you can do it quicker. All right, number 25 next. All right. You're on time. Good so far. Assume that vinegar is 0.852 molars solution of acetic acid. Okay. What volume of 0.2136 molar sodium hydroxide would be needed to completely neutralize 6.89 milliliters of vinegar? All right. So let's put what we know. 0.852 molar. That's the concentration, the molarity of the acid is 0.852 molar. Okay. And the volume of the vinegar is 6.89 milliliters. Okay. Molarity of the base is what? Molarity of the base is 0.2136. 0.2136 molar. And we want to know the volume of the base. Right? Yeah. Okay. Since acetic acid has 1 proton per molecule, sodium hydroxide has 1 hydroxyl, then this formula will work. Molarity of the acid, volume of the acid equals the molarity of the base, volume of the base. Okay. And the reason that works is if you convert these to normality, there's only 1 hydrogen here, so this is also normality of the base of the acid. And this is also the normality of the base. Right? So we just substitute in here and they're exactly the same values. Okay, either way. So if we're solving for the volume of the base, then the normality of the acid times the volume of the acid over the normality of the base equals what? Well, the normality of the acid is 0.852 molar, and its volume is 6.89 milliliters divided by 0.2136 normal. See, that should be normal. There we go. Now that's the thinking part, as usual. We're going to crunch some numbers. Yep. And this is 27.5 milliliters of base. Okay. That's number 25. (26) The reaction between 200 milliliters of 0.1 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride. For this reaction, the concentration of silver ions in solution after the reaction is complete is. Okay, so let's put that reaction back up here. Right, we had silver nitrate. They gave silver nitrate first, so we'll put them in that order. Silver nitrate in solution plus sodium chloride in solution yields what? They put them in order? They want silver ions in solution. Let's put silver chloride solid plus sodium nitrate in solution. And we found out earlier that this is already balanced. Okay, we've got 200 milliliters of 0.1 molar silver nitrate, 200 milliliters of 0.1 0.1 molar silver nitrate, and sodium chloride is 95 milliliters of 0.1 molar. Oops, didn't mean to do that. 0 molar. Okay. The question has to do with silver ions after the reaction. What's the concentration of silver ions? Well, first, let's determine whether or not there are any silver ions left. If these are exactly the same concentration, then you have, this is the limiting. It's a smaller volume at the same concentration, and this is 1 to 1. So this one is going to be limiting. And this is going to be excess. So that means there are going to be some silver ions left over. All right, let's see how many. Well, if we multiply 0.1 times 200, we get 20 millimoles of silver nitrate. Okay. And this one, we get 9.50 millimoles of sodium chloride. Okay. So, since these are 1 to 1, and this is also 9.50 millimoles of silver chloride are produced. Okay. That means 9.50 millimoles of silver have been consumed. 9.50 millimoles of silver ions used. Okay. How many did we start with? 20 millimoles of silver nitrate is 20 millimoles of silver ions, right? Because it's 1 to 1. For every one of these, you get one of those. Right, so how many are we left with? 9.50 subtracted from that is 0, 5, 9 from 9 is 0, 1. Is that right? Yeah. Millimoles of silver remain. All right. Now, the questions look like they're questioning concentrations. Okay. Well, maybe we don't need to know that. 1 mole of silver. We may be able to answer the question already without even calculating concentration. So let's look at A through E. So what does A say? The concentration of silver ion in the solution after the reaction is complete is 0.1 molar. Oh, we better calculate the concentration then. So millimoles divided by milliliters is molarity. So 10.5 millimoles of silver divided by how many milliliters? 200 plus 95. 295 milliliters. Now, how do I know that's molarity? Well, this is milli, and that's milli. The millis cancel, and moles divided by liters is molarity. So, 10.5 divided by 295 is 0.0020356 molar silver. That's what remains. Okay. So A says 0.1 molar silver ion does not participate. That's false. We just proved that silver participates and its concentration is a lot less than 0.1. Less than 0.1. Some, but not all of the silver ions are used to make the precipitate. That is true. That is true. And the rest are probably false. C, we'll just look at them while we're here. Greater than 0.1. Yeah, okay. For every 1 mole of silver nitrate, there are 2 moles of silver ions. No, that's not true. For every 1 mole of silver nitrate, there's 1 mole. Can't be true. You can't make something out of nothing, right? Conservation of mass. Less than 0.1 molar, yes. D is, that statement is true, but even though silver ions do not react, they are diluted. All right, silver ions do react. So D can't be true because the second part of the statement is false. And then E, 0 molar. All the silver ions are used up to make the precipitate. Nope, because we proved that silver nitrate is excess. There will be silver left over. So B is the correct answer for that one. All right. Uh, 29. A nitric acid solution containing 71% HNO3 by mass has a density of 1.42 grams per mil. How many moles of HNO3 are present in 2.36 liters of this solution? This is a dimensional analysis problem. Pure and simple. We're starting off with 2.36 liters of solution. 2.36 liters of solution. What we want to know is, what is that mass of solution first? So 1.42 grams per milliliter, right? So let's change this to milliliters. Right? That changes to milliliters. Now we can multiply it times 1.42 grams per milliliter. 1.42 grams per milliliter. And this is still grams of solution. Right? So that gets rid of milliliters. Now we have grams of solution. Now we want to convert grams of solution to grams of HNO3. So for every 100 grams of solution, we have 71, correct? 71.0 grams of HNO3. Okay. Now we want to convert grams of HNO3 to moles. And we need the molar mass, which I can't remember, so we have to add it up again. So hydrogen is 1.01 gram per mole. Nitrogen is 14.01. And oxygen is 3 times 16. There's your total. Let's see, 48 for oxygen and 14.01. Let's see, and 1.0. That's 63.02 grams per mole. There we go. That'll tell us the number of moles of HNO3 that we have in this problem. 2.36 times 1,000 times 1.42 times 71 divided by 100 divided by 63.02. And that is 37.3 significant figures, 37.8 moles. Okay, and that's A. All right. 29. Who's next? Let me skip a few. Here we go. 38. You have two solutions of sodium chloride. One is 2 molar, the other is 5 molar. You have much more of the 5 molar solution, and you add the solutions together. Which of the following could be the concentration of the final solution? All right, so the first one is 2 molar. So molar 1 equals 2 molar. And molar 2, solution 2 is 5 molar, right? 5 molar. Okay. Let's see. You have much more of the 5 molar solution. So the volume of this one is much, much greater than this one. Excuse me. Right. The volume of 2 is much greater than the volume of 1. Add the two solutions together. Which of the following could be the concentration of the final? All right. When you add two solutions together at different concentrations, you're going to dilute this one and concentrate that one, right? So the actual number is going to be in between the two. So the M of the mixture is going to be, actually, will be between 2 and 5. We know that, right? So we can look at the possible answers. Let's see, A, B, C, D, and E. The first one is 7.20 molar and 3.5 molar, 2.90 molar, and 4.80 molar, and 7 molar. Okay. Now, if it's going to be between 2 and 5, we can eliminate this one. That's too much. We can eliminate this one. That's too much. Okay. Also, what we can do is say these are between 2 and 5. And if the volume of the 5 is much, much greater than the 2, then the highest concentration is the likely concentration. So it won't be this one, it won't be that one, it's probably this one, the largest one available. Right? That was a sort of a semi-quantitative logic problem. All right, let's see, we did that one already. 50. Okay. What's the normality of 1 liter of sodium hydroxide solution that contains 18.2 grams of sodium hydroxide? All right. First off, sodium hydroxide only has 1 equivalent per molecule, 1 hydroxyl. So if we calculate the molarity, it's the same as the normality. So what we're going to do is find out how many moles of sodium hydroxide are in that liter. 18.2 grams of sodium hydroxide converted to moles. Let's see, grams per mole. So sodium hydroxide would be, I know we did this one before, 23 for sodium, 16 for oxygen, and 1.01 for hydrogen. Let's see, that's 710, 40.01. Divide that into 18.2. So that's 0.455 moles. I can do better than that. Of sodium hydroxide. Per what? In 1 liter. Right. Yeah, 1 liter. That means it's 0.455 molar. And since sodium hydroxide has 1 equivalent per molecule, that's also 0.455 normal. Okay, and that's A. All right, 52. You have, oh, we already did this one. Yeah, sorry, we already did this one. Let's go down to 55. The following acid-base neutralization, 1.61 grams of solid HC6H5O, which would be phenol. I'm pretty sure that's what that is. Neutralized 11.61 milliliters of aqueous sodium hydroxide solution based upon this reaction. Calculate the molarity of the base solution. All right, so let's put the reaction up here. Right, we had sodium hydroxide, which is aqueous, plus HC6H5O, and that's put in solution. Right, we know that it's 1.61 grams. 1.61 grams in solution. And it was able to neutralize, well, let's see, it produced water, of course, and the salt, which would be sodium, sodium C6H5, phenolate. And this is, yeah, that's in solution also. Okay, so 1.61 grams of that. Sodium hydroxide, the details are 11.61 milliliters. 11.61 milliliters. And we want to know the concentration of sodium hydroxide. All right. 1.61 grams of this is how many moles? We need to know the molar mass of that one. So 6 hydrogens and 6 carbons and 1 oxygen. That's the molar mass of that compound. So this is 94.12 grams per mole. And then we want to convert that number of grams, 1.61 grams, to moles. So 94.12 goes in the denominator. We divide that into 1.61, and I get 1.71 times 10 to the minus 2 moles of the acid. Okay, so since these are 1 equivalent per molecule, 1 equivalent per molecule, we can use molarity of the base times the volume of the base equals the molarity of the acid times the volume of the acid. And we want to find out the molarity of that one. So let's solve it for that. molarity of the acid times the volume of the acid over the volume of the base. Oh, we haven't done the molarity yet. Okay. We start off with 1.61 grams of solid phenol. And we neutralize it with 11.61 milliliters of aqueous sodium hydroxide. We have to assume that the volume is 11.61 milliliters, final volume. Otherwise, we're stuck, right? We can't go anywhere without volume because we need to divide this, moles, divided by the volume, which is 11.61 milliliters, 0.61 times 10 to the minus 3 liters, right? I was just changing that milliliters to liters. And this is 1.473 molar. Okay, now we can find out the molarity of the base. Molarity of the acid is 1.473. Volume of the acid is you know what? I'm still stuck because there's no volume of the acid. All right, we're gonna have to approach this differently. That was the wrong approach. This many moles of acid will neutralize the same number of moles of sodium hydroxide. So the moles of sodium hydroxide is equal to the moles of the acid because they're 1 to 1. Okay. So we have 1.71 times 10 to the minus 2. Actually, yeah, that's fine. Moles of that of sodium hydroxide. Divided by 11.61 times 10 to the minus 3 liters. That's the molarity of the base. 1.71. Yeah, 1.47 molar. So that's E. Yeah, I started barking up the wrong tree and then I decided, wait a minute, this is a stoichiometry problem first. So the moles of acid equals the moles of base. If we have the moles and the volume, we can calculate the concentration. 59. What volume of 0.176 molar sodium sulfide solution contains 1.01 grams of sodium ions? All right, if we have 0.176 molar, 0.176 molar sodium sulfide, and we want 1.01 grams of sodium ions. 1.01 grams of sodium ions. Okay, the question is, what's the volume of the solution? The volume of that solution is the question. So in order to find the volume of the solution, right, molarity equals moles over volume. Volume equals moles divided by molarity. So we got the molarity. we need the number of moles of that compound. Right? This will give us the number of moles of sodium ions. Why? Because the sodium ion is a +1 charge because it lost an electron. How much does an electron weigh compared to the sodium atom? Not much. So we're going to use the molar mass of sodium to convert this to moles of sodium ions. Grams, moles. I believe that's 23. Yeah, 23. All right, 23 into 1.01 is, let's put it over here, 4.39 times 10 to the -2 moles of sodium ions. Now we need to convert that to moles of sodium sulfide. Mole sodium ions. So for every 1 mole of sodium sulfide, we have 2 moles of sodium ions, right? 2 to 1. So we divide this one by 2, and that's 2.196 times 10 to the -2 moles of sodium sulfide. Now we can solve for volume. 2.196 times 10 to the -2 moles divided by 0.176 molar. And that gives us 0.125 liters. Is it in liters? Yeah. So that's key. There you go. 59. Let's see, what's next? 62. Okay, I'm running out of time here. Sodium phosphate and lead nitrate. What's the concentration of phosphate ions left in solution? All right. So these compounds are given to us in words, the names. We have to write the compounds in order to balance the equation. Right? So there's another case where if you don't know how to write the compounds, how to write their formulas, then you can't solve this problem. Okay, we're reacting sodium phosphate in aqueous solution and lead 2 nitrate. In aqueous solution. And that's going to make lead plus phosphate. Right? If this is a 3- and this is a 2+, put the 3 over here and the 2 over there. Okay. Now you can look this up, and that's a solid. That's our precipitate. And then sodium nitrate is what's left over. Sodium nitrate is aqueous solution. All right, so we got our compounds written. We need to balance the equation. Let's see if I can do this without writing the budget. 3 sodiums. Most of these double replacement reactions like this are easy to balance without the budget. So 3 sodiums means 3 nitrates. Oops. If I put 3 here, that's going to be 6 nitrates. So let's start someplace else. Let's start with nitrates. No, let's start with lead. There we go. 3 leads gives you 6 nitrates. Makes 6 sodiums and 2 phosphates, 2 phosphates, 3 leads. Now we're balanced. 2, 3, 1, and 6. Okay, next. What are the conditions? 15 milliliters of 0.3 molar sodium phosphate. 15 milliliters of 0.30 molar sodium phosphate and 20 milliliters of 0.2 molar. 20 milliliters of 0.2 molar. Okay. What's the concentration of phosphate ion left in solution? All right. We have to find out which one is limiting. So we got to do moles here. Let's see. If we convert, if we say 0.3 times 15, I think that's 5. Yeah, no, 4.5. 4.50 millimoles of that compound. And this is 20 times 0.2 is 4 millimoles. Then let's convert this one to lead 2 phosphate and this one to lead 2 phosphate and find out which one is limiting. All right. So if we take this one, 4.50 millimoles of sodium phosphate, and we're going to convert it to lead 2 phosphate. The ratio is 1 here, 2 there. So let's see, flip that and divide by 2, it's 2.25. 2.25 millimoles of lead 2 phosphate. That's how much this would produce if it's limiting. How about the other one? Right, 4 millimoles, in this case, of lead 2 nitrate. Now we need, lead 2 nitrate. And we want to end up with the same product. Okay. So again, we have 1 here and we have 3 here. Correct? Okay, so 3 into 4 is 1.333. 1.33. That's good enough. Millimoles of lead phosphate. Okay. So this is the limiting one, and this tells us how much lead 2 phosphate is produced. Right? So if it's 1.33 millimoles of lead 2 phosphate, how much phosphate was used? Well, for every one of these, you have 2 phosphates. Right? So if 1.33 millimoles of this were produced, that's 2.66 millimoles of phosphate ions were used. All right. How many phosphate ions did we start with? Well, that's over here. 4.50 millimoles of this compound, 1 to 1. So every one of these, you have 1 of those. So we actually have 4.50 millimoles of phosphate to start. And then we subtract the amount that was used, 2.66, which would be, let me use my calculator, 1.84 millimoles of phosphate remain. Okay. Now, if we divide millimoles by milliliters, we'll get molarity. So how many milliliters do we have? Well, we got 15 plus 20. We have 35 milliliters. So the concentration of phosphate is, let's see, it's in the standard notation. So let me see, move my decimal to the left, 0.053 molar phosphate. Anything close to that? Yeah, A is the closest one. There's some rounding error in there. All right. 64. All right, I'm almost out of time. $64. Okay. When a solvent has dissolved all the solute it can at a particular temperature, it's said to be saturated. That's definition, saturated. All right, so D is the answer to this one. 65, we're going to do that one also. 65. If you mix 20 milliliters of 3 molar sugar solution with 30 milliliters of 5.57 molar sugar solution, you will end up with a solution of what concentration? Right. We're not diluting with solvent. We're diluting with another concentrated sugar solution. So what we have to do is find out how many moles are we putting in of sugar from both of them, and then divide by the total volume. All right, so 20 milliliters times 3 molar would give us 60 millimoles of sugar, and then 30 times 5.57 molar. I'll use my calculator for this one. Is 67.1 millimoles. So the total millimoles is 227 millimoles of sugar. And per what volume? 20 plus 30. 50 milliliters. Remember, millimoles divided by milliliters is molarity. So we have 4.5 4 molar. There you go. That's A. All right, that was 64 and 65. And I'm officially out of time. Let me see how many more we got to go. Let's see, 74. That's one, just one more. So I'm going to do this last one and we'll be done. 74. 15 milliliters of 0.3 molar sodium phosphate reacts with 20 milliliters of lead to. That's the same equation we had up there before. What's the concentration of nitrate ions left in solution after the reaction is complete? For this one, nitrate is a spectator. So all the nitrate we start with is the nitrate we end with. So really all we have to do is find out how many moles of nitrate do we start with. Right, we have 0.3 molar lead-2 nitrate. So lead-2 nitrate would be, let's see, 2 and 1. That means this is 2. Go. Lead-2 nitrate. And we have, let's see, 0.3 molar times 20 mils. .3 molar, which would be, I think, 6. Yeah, this would be 6 millimoles of the compound, right? But we have 2 nitrates for every one compound. That means 12 millimoles of nitrate. Now we need the total volume. So we have 20 milliliters of this. We have 15 milliliters of the other solution, which means 35 milliliters. And that's 0.171 molar. Or rounded off, 0.17. Okay? That saves some time. We didn't have to actually write the equation. We just needed to know the compound formula. All right, that's it. So next Thursday, your exam will be due by midnight. And when we meet on Thursday, or when I'm here on Thursday, I'll cover the next chapter, which is 13. I'll cover chapter 13, which is gases. And then you'll find out how to solve the rest of that problem we covered at the very beginning of this session. That's it for today.